Today we're going to talk about the power series, and specifically the interval of convergence and the radius of convergence. So we're already familiar with this idea from infinite geometric series. So this is an infinite geometric series with a common ratio of negative 5x. So the interval of convergence would be between, when negative 5x is between negative 1 and 1, which is going to be when x is between negative 1/5 and 1/5. That's our interval. The radius is going to be the distance from the center. So if I were to put this on a number line, we'd have 0, negative 1/5, positive 1/5. Just like in a circle, the radius is the distance here, or half the distance between the two. So the radius here is 1/5. Name the function, so a1 over 1 minus r. My a1 is 1 over 1 minus r, so we're going to have plus 5x. Okay, another geometric series. Our common ratio here is we're multiplying by 2 on the outside and then a 2 minus x. So the interval of convergence is going to be when that, which if I multiply is 4 minus 2x, is between negative 1 and 1. So subtract 4. And then divide by a negative 2. So negative 5 divided by negative 2 is positive 5/2, but this will switch. So our interval is going to be 3/2 is less than x is less than 5/2. The radius is going to be the half of the distance between these two. So 5/2 minus 3/2 all over 2. So 2/2 over 2, which is 1 over 2. The function a1 over 1 minus r is going to be 3 over 1 minus 2 times 2 minus x, which you could simplify or leave it just like that. Okay, an approximation is said to be accurate to n decimal places if the magnitude of the error is less than 0.5 times 10 to the negative n. We're going to be talking more about error next class. For any power series in x minus a, exactly one of the following is true. Okay, the series converges for just a, the series converges absolutely for all a, or the series converges for a finite interval. It converges for an open interval, diverges outside of that interval, and then we have to look at the endpoints. So let's look at some examples. Okay, so we've got a bunch of different examples where we're going to find both the interval of convergence and the radius of convergence. So notice we have a sigma notation with k, and we have an x here. To do this, we're going to use the ratio test for absolute convergence. Okay. In the ratio test, for absolute convergence, we're looking at the limit as k goes to infinity of the absolute value of the kth plus 1 term over the kth term. Because it's the absolute value, this negative 1 to the k is just going to go away, so I'm not going to worry about that. So we're going to have x to the 2k plus 1 over 2k plus 1 factorial all over x to the 2k over 2k factorial. Okay, so then we've got some algebra ahead of us. Okay, so in the top, this is going to be x to the 2k plus 2. So I'm going to write that as x to the 2k times x squared over, this would be 2k plus 2 factorial. So I'm going to have 2k plus 2 times 2k plus 1 times 2k factorial. Okay, I went all the way down to there because then that's going to cancel with the 2k factorial. Okay, and then we get to cross off a bunch of stuff. So x to the 2k goes away. The 2k factorial goes away. At this point, I'm going to pull the x out of the factorial because the limit is involving, or out of the absolute value. Okay, everything left is positive, so we're going to have 1 over, if I FOIL this, 4k squared plus 7k plus 2. Well, what is that limit? This is going to be 0. And we're interested in when this is less than 1. Well, it will always be less than 1 because it's always going to be 0. So it converges for all values. So we're going to say the interval is from negative infinity to infinity. The radius is infinity. All right, let's look at the next one. Take the limit as n goes to infinity. Ignore that. In the top, we're going to have 2n plus 1 factorial x to the n plus 1 over 2 to the n plus 1 all over 2n factorial x to the n over 2 to the n. So in the top, this is again that 2n plus 2 factorial. So we're going to have 2n plus 2 times 2n plus 1 times 2n factorial x to the n times x to the 1, 2 to the n times 2 to the 1, and then multiply by the reciprocal. Okay, cross stuff off. So 2n factorial goes away, 2 to the n goes away, x to the n goes away. So I'm going to again pull the x out with the absolute value. So that's going to leave me with 4n squared plus 7n plus 2 all over 2. Okay, well, absolute value of x times infinity will be less than 1 at one location when x is 0. Okay, so this one is only going to have a single value when x equals 0. So we have x to the k over the square root of k. So we're going to have x to the k plus 1 over the square root of k plus 1 over x to the k times square root of k. just like always, this will be x to the k times x over the square root of k plus 1. It's the square root of k over x to the k. Don't get to cross off as much stuff this time, but that's all right. So we get absolute value of x times the limit as k goes to infinity of the square root of k over the square root of k plus 1. Well, as we go to infinity, this is the same degree, so this is just going to go to 1. So we want that to be less than 1 in order for it to be convergent according to the ratio test. So we want -1 to be less than x to be less than 1. At this point, we can identify the radius is 1. Okay, what we have to do next is test the endpoints. So what we're going to do is we're going to take our sigma notation, and for the x, we're going to plug in -1, see if that series converges. Then we're going to plug in 1 and see if that converges. So when x equals -1, our new series is going to be -1 to the k minus 1, -1 to the k, over the square root of k. So does this converge? We can multiply these together since they have the same base. That means we're going to add the exponents. So this will be -1 to the 2k minus 1. Okay, well, no matter what value I plug in here, I'm going to get an odd number, which means this is always going to be negative. So this is -1 over root k. So it is a p series. It's negative, but it's still a p series with p equaling 1/2, which means this is divergent. So -1 is not included in the interval, but perhaps 1 is. Okay, so we plug 1 into that location. 1 to the k is just 1, so this is just -1 k minus 1 over square root of k. This one will alternate. Okay, so we are going to use the alternating series test. In the alternating series test, we need two things to be true. We need the limit as k goes to infinity of everything except for the alternating piece to go to 0. And we need it to be decreasing. Well, 1 over square root of k is just k to the -1/2. So this is going to be -1/2 k to the -3/2, which will be less than 0. So that one checks out. So this one converges. So our interval does not include the -1, but does include the 1. So we're going to look at the limit as k goes to infinity. X minus 4 to the k plus 1 over k plus 1, well, plus 1, so k plus 2. All right, let's go through our algebra. We're going to have x minus 4 to the k times x minus 4 over k plus 2 squared times k plus 1 squared over x minus 4 to the k, absolute value. So that goes away, that goes away. This time I'm going to pull x minus 4 out with the absolute value. Which leaves me with k plus 1 squared over k plus 2 squared. Okay, well that limit is just going to be 1. And we want that to be less than 1 for the ratio test to give us a convergent result. Well, that means we want negative 1 to be less than x minus 4 to be less than 1, and then we'll just add 4. So again, from here we can determine our radius. Distance between those is 2, so my radius is 1. And then we're going to test the endpoints by plugging them in to our equation here. Find some space here. So we're going to test x equals 3. So we have the negative 1 to the k. If I plug in 3, we have 3 minus 4, which means I have negative 1 to the k over k plus 1 squared. Well, negative 1 to the k times negative 1 to the k is going to be negative 1 to the 2k, which is going to just be 1, always, because it's always be positive. Okay, so this one, if I were to FOIL it out, we're just going to have a quadratic. So we could compare it to k squared, which is going to converge. So I'm just going to say p series, p equals 2, which means this converges. Okay, then we're going to test x equals 5. Okay, when we plug 5 in for this, we're going to get 1 to the k. So this is just going to be negative 1 to the k over k plus 1 squared. Well, if this one converges, the alternating one also has to converge, because it converges absolutely if the absolute value one converges. Okay, so our interval will be 3 is less than or equal to x is less than or equal to 5. Both endpoints are included here. All right, to our next one. We'll have 3/4 to the k plus 1, x plus 5 to the k plus 1, over 3/4 to the k, x plus 5 to the k. So we're going to have 3/4 to the k times 3/4, x plus 5 to the k times x plus 5, those go away, those go away. So I'm going to pull out the x plus 5. which leaves me with, I crossed off everything here except for 3/4. So the limit as k goes to infinity of 3/4 is 3/4. And we want that to be less than 1. So we want negative 4/3 to be less than x plus 5 is less than 4/3. Okay, so this means my radius is 4/3, so I'll go ahead and okay, and then we're just gonna add or subtract 5 from both. So I'm gonna subtract 15/3, so negative 4/3 minus 15/3 is negative 19/3. And 15/3 minus 4/3 is, or other way around, negative 11/3. Okay, so then we need to test the endpoints. Okay, I'm gonna let x equal negative 19/3. So my series, we're going to have 3/4 to the k. X is negative 19/3 plus 5, so I'm going to make that 15/3 to the k. Okay, well, since these have the same exponent, I can multiply the bases. So 3/4 times negative 4/3 is a negative 1. Negative 1 to the k diverges. It just keeps bouncing between 1 and negative 1. What about when x equals negative 11/3? Okay, so again, 3/4 to the k, negative 11 plus 15 is going to give me 4/3. So this is 1 to the k, which would just be 1 plus 1 plus 1 plus 1, which also diverges. So my interval is negative 19/3 is less than x is less than negative 11/3. We do not include either endpoint here. I'm going to skip over this one. It is a very involved one, so I'll do it in class to show you. But you can copy down the answer from the PDF, and we're going to move on. Determine the interval and radius of convergence of x to the n over n factorial. The limit as n goes to infinity of x to the n plus 1 over n plus 1. And I'm just going to go ahead and jump to the multiply by the reciprocal. So x to the n times x over n plus 1 times n over x to the n. Pull out the x. Which leaves me with n over n plus 1. So the absolute value of x times 1, that limit is 1, is less than 1. So negative 1 is less than x is less than 1. So let's test the endpoints. When x equals negative 1, I have the series negative 1 to the n over n, which is happily the alternating harmonic. And we know from previous tests, this is convergent. And we can always say that if it's the alternating harmonic, it's convergent. What about when x equals 1? We have 1 to the n over n. Well, that is 1 over n, which is harmonic divergent, because it is not the alternating version. Okay, so our radius is 1. The interval, we are including the negative 1. We are not including the positive 1. Okay, this leads us to our next problem that says determine the radius and interval of convergence of f prime of x. When we're taking the derivative, the open interval is guaranteed. So negative 1 to 1 holds true. But when we take the derivative, we may lose an endpoint. So let's first take the derivative. X to the n over n. So that's going to be n x to the n minus 1 over n, which is just x to the n minus 1. So my series is now x to the n minus 1. Negative 1 to 1 is guaranteed, but it may lose its endpoint. So we need to test the negative 1. So if I have negative 1 to the n minus 1, that's that series. It's just going to keep flip-flopping between negative 1 and 1, so the series diverges. Okay, so my radius is always 1. That's not going to change. The interval, however, is now just negative 1 to 1, not including either endpoint. The interval and radius of convergent for the power series, 1 over 1 plus x squared. So we're back to where we started. This would be an infinite geometric series with a common ratio of negative x squared. So it will converge when negative x squared is between negative 1 and 1, which is when x is between negative 1 and 1. So my radius is 1, and this is my interval. Okay, but now we're going to examine the tangent inverse. Why is this part B? Well, tangent inverse is equal to the integral of 1 over 1 plus x squared. Okay, the derivative of tangent inverse is 1 plus 1 over x squared. So we're going to do the integral of the power series. The open interval is still guaranteed, but in this case it may gain an endpoint. So this power series, IA1 is 1, so this is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So that's just going to be negative x squared to the n. And then we will integrate. So this will be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So what's happening in this series? We're alternating signs. I'm going to have negative 1. I'm going to leave it n for this minute. X to the odd numbers we can get from 2n minus 1. If we're starting at 1, that means n is 1, but we want this first one to be positive. So I'm either going to add 1 or subtract 1 from that negative 1 part, all over 2n minus 1. And you can do 2n plus 1, which would make this 2n plus 1. It's just going to affect your starting value. So let's put this new series in sigma notation. Okay, I said we're starting at 1 to get that term. All right, so what we need to do here is test the endpoint. that we may gain, which is going to be the 1. So that series, -1 to the n plus 1, 1 to the 2n minus 1 over 2n minus 1. Well, that piece is just always going to be 1. So this is -1 to the n plus 1 over 2n minus 1. So we're going to, again, use the alternating series test. So the limit as n goes to infinity of 1 over 2n minus 1 is 0. This derivative is -2 over 2n minus 1, which will be less than 0 because of the negative. So this one converges. So my radius is still 1. The interval now includes both endpoints. So that is radius and interval of convergence.